So I'm going to introduce the idea of electric fields to you guys. As always, this is complementing the reading in the books. Explain a little bit, show you a couple examples, and hopefully that'll help you understand what you're reading and what we're doing in class a little bit better. So anywhere you have charges, you have electric fields. So one single charge, you can have a field. You can have fields between two charges or three charges, and they can be attractive, which is what the picture in B shows on the screen. And you can also have where the field is a repulsive field, and you'll see pictures of that, I guess, in lab or in your book, and it kind of looks like a pair of squash spiders if it's between the two charges. And so electric fields are vector quantities. The direction of the field is pointing away from the positive charge, or you can think about it as if what would happen if I threw a positive charge into this field? Which way would it go? And a lot of times you'll hear it called a test charge. And so the field line density indicates how strong the field is. So you can see closer to the charge, the lines are closer together, further away from the charge, they're further apart. And so that should make sense. And then when you have a whole lot of charges, you get a whole lot of charge density, and you're going to end up treating this with some calculus. And the calculus examples will be in an additional video. So we'll start off with a nice, easy equation. Electrical fields will cause a force. And so it's real simple. It's the charge times the electrical field. A lot of times when you're actually working these problems, you'll be finding the field where there's an electrical force. So it'll give you the charges, it'll give you the distance apart, you can find the force, and then you can find the field. And so that's generally how that works. And so here are some other equations. Don't let the calculus scare you any. Like I said, I will have an additional video with some calculus examples in it. For the most part, you can simplify these down when you have real numbers, and end up with some of the special cases, and I'll show you those in a minute. Notice that they have the permittivity of free space in them. There are some interesting symbols in here, so that lambda, sigma, and rho are densities of charge. And so lambda is a charge per unit length, and you're going to deal with that when you're talking about a wire or a charged rod. Sigma, a charge per unit area, so that's going to be your flat plates. You're going to have discs and plates. And then the rho is charge per unit volume, so now we're talking about spheres or clouds. Probably not clouds because they don't have a nice volumetric shape, but you can have a nice sphere. Or maybe a cube, but usually they'll be spherical. And then a couple minutes ago I mentioned that there were special cases, and these are a little bit easier to deal with. And a lot of times, because charges are so tiny and wires are kind of big, you can call it an infinite wire. You can have an infinite plane. And these are good estimations of what would happen, and so you can use them. So you're going to be using the field of an infinite wire, and then the field on an infinite plane. So in this example, we're going to find the electric field due to an alpha particle, measuring it from the location of an electron that's placed 10 times 10 to the minus, 1 times 10 to the minus 10 meters away, or 1 angstrom away from the alpha particle. And you're going to use the equation for the electric field, which is force over charge. And when you work out all of the derivations and cross everything out, you end up with kq over r squared. And so plugging in the numbers and doing the algebra, you end up with 2.8 times 10 to the 11th newtons per coulomb. It's kind of strange because you're going to end up with a really big number when we've been working with really teeny tiny numbers for Coulomb forces. So just keep that in mind. There's nothing wrong with that. So for this example, we're going to talk about two conducting parallel plates. They're going to be placed 1/100th of a meter apart. They're square and half a meter on each side. And 10 to the 10th electrons move from one plate to the other, and we need to find the field between the plates. So you need to start off by finding the charge density. How much is the charge per area on the plates? And then use the electric field equation, once you have that, to find the electric field. You will need the permittivity of free space for this, 8.9 times 10 to the minus 12 Coulomb squared Newton squared per meter, or Coulomb squared per Newton squared meter squared.